Topics in the History of Mathematics, Audio Cassette 4. You should listen to this in connection with your study of Unit 7. This is an illustrated talk by Dr. Penelope Goke, Research Fellow of Linacre College, Oxford, and is entitled Harmony in the 17th Century.
The word harmony had many important connotations in the 17th century. These still survive today to a limited extent. We use the term harmony most often in a musical context to denote the combination of chords which sound pleasing together. In a more general sense, harmony signifies agreement, balance and proportion between things. In the 17th century, the connection between the musical sense of harmony and its wider significance was much more real and explicit than it is today. At this time, it was generally believed that there were two types of music, practical and speculative. Practical music was the art and science of audible music, that of voices and instruments. It was subordinate to the science of speculative music, a philosophical conception about the order and structure of the cosmos and the body and soul of man. These forms of inaudible music were known as world music and human music. Practical and speculative aspects of music were interconnected by means of number and proportion. Following Pythagoras, music was considered a branch of the quadrivium, a mathematical science, along with astronomy, geometry, and arithmetic. In the Renaissance, many original Greek writings on music were rediscovered and given new life by philosophers, humanists, mathematicians, and musicians. The wide range of sources available enabled individuals to use ancient authority to support different attitudes and beliefs about music and its meaning. For some, such as Kepler, the texts which emphasized the metaphysical dimension of music were most significant. For others, particularly musicians, ancient writings on the performance and practice of music held most fascination. While at first it seemed possible to reconcile philosophy and practice, the two appeared to have diverged by the end of the 17th century. Until the 16th century, the dominant music theory was Pythagorean Platonic, usually defined as Neoplatonism. This was a wide-ranging, eclectic system of ideas, loosely derived from Plato's dialogues. In general, Neoplatonists weren't interested in music for its own sake, but for what it could teach the philosopher. Inspired by Plato's insistence on the need to look beyond the imperfect world of the senses, they believed music could provide a key to understanding the harmony of the universe. According to such a view, practical problems of the musician were of little or no interest. The proportions of the true scale were fixed and unchanging. Musical sounds could only imitate true harmony. What were the implications of this for musical practice? You'll remember that the Greeks had had quite a sophisticated debate about the nature of musical harmony. In their view, intervals of the octave, fifth and fourth were consonant or harmonious because of the simple ratios of string lengths that were involved in their production. From this initial insight, they'd built up a variety of theories designed to explain the entire division of the octave. Throughout the Middle Ages, the Pythagorean scale was that accepted by most music theorists. The correspondence between the simple ratios using the numbers 1 to 4 and the consonances was demonstrated by the division of the monochord. First, the octave, with a ratio of 2 to 1. Next, the fifth, with a ratio of 3 to 2. Finally, the fourth, with a ratio of 4 to 3. According to tradition, Pythagoras had also experimented with weights attached to strings, pipes of various lengths, and partly filled glasses. In all these experiments, he supposedly found that the same ratios caused the same consonances. Neoplatonists believed that the explanation for the beauty of these consonances, and indeed the beauty found in all arts, lay in the power of numbers themselves. Numbers were the ultimate constituents of reality. In the mid-16th century, the Italian music theorist Zarlino extended the numbers which produce consonances to include 5 and 6, in order to allow the thirds and sixths used in contemporary practice to be included among the consonances. Modern polyphony appeared to Zarlino to be fully reconciled with ancient authority. The pure major third has a ratio of 5 to 4. The minor third has a ratio of 6 to 5. The major sixth is next with a ratio of 5 to 3. The minor sixth is more of a problem. It has a ratio of 8 to 5. For the purposes of Zarlino's argument, which only uses the numbers 1 to 6, 8 has to be regarded as 2 times 4. Zarlino's numerological explanation was challenged by Vincenzo Galilei, Galileo's father, in the 1580s. Vincenzo was a music theorist, a lutenist and philosopher. But before we consider his attack on Zarlino, it's important to note that Platonic music theory had already been questioned by Aristotle and his followers. Aristotle rejected the harmony of the spheres and the mystical speculative concerns of the Platonists. He considered music to be a branch of physics rather than metaphysics, dealing with sound rather than number. Music wasn't a mathematical science, but was a vocal art linked to poetry. Its power lay in its ability to arouse emotion and action. Aristoxenus, a follower of Aristotle, established a theory that was to deal with actual music rather than metaphysics. Musical intervals were to be judged by the ear rather than the reason. Until the Renaissance, this alternative view of music was little known. But once it became available in translated texts by the late 16th century, some musicians and theorists dared to challenge convention. The debate over whether music should always be judged by the ear alone, or whether it should be dictated by reason and authority, had important implications, not only for musical practice, but also for science. Vincenzo Galilei, for example, wasn't satisfied with a purely numerical explanation for harmony, nor did he think that ancient authority should be accepted without question. He began to inquire into the physical nature of sound and the production of individual notes by strings and pipes, and made a surprising discovery.
I wish to point out 2 false opinions of which men have been persuaded by various writings and which I myself shared until I ascertained the truth by means of experiment, the teacher of all things. They believe that the weights Pythagoras attached to the strings, better to hear the consonances, were the same as those of the hammers from which he first heard them. Now, that this could not in any way be so, experiment, as I said, demonstrates. For if someone wished to hear from 2 strings of equal length, thickness and quality the sound of the octave, it would be necessary for him to suspend weights not in the duple, but in the quadruple proportion.
In other words, if 2 strings of the same length and thickness are stretched by weights, to make one an octave higher than the other, a weight 4 times larger must be used, giving a ratio of 4 to 1. Vincenzo used this experiment to challenge numerological explanations. He found that physical factors were responsible for determining the pitch of a string, particularly its material, tension and thickness. Music was thus an important part of the development of experimental science, which his son Galileo continued. The context of Vincenzo's scientific activity is important. It arose out of his involvement with the Florentine Camerata, a group whose members disliked modern polyphony and who wished to recreate the powers of ancient monody. The aim of this type of music wasn't to produce pleasing harmonies, but was to move the passions and emotions through a simple monodic line, as we hear in this piece by Giulio Caccini. Yet the new monodic style wasn't appreciated by everyone at the time. Johannes Kepler, for example, preferred the polyphonic music of Orlando di Lasso, a musician who'd been at the court of the Holy Roman Emperor at Prague some years before Kepler arrived there in the late 1590s. Compared to the simple line of Caccini's music, listen to the richness and complexity of this piece by Lassus. Both practical and speculative, was complex. Like Vincenzo, he believed that music theory should follow contemporary practice rather than receive tradition. He wrote in his Harmonici Mundi of 1619,
"The Pythagoreans were so addicted to philosophizing in numbers that they failed to keep the judgment of their ears, though it was by means of this that they had initially been brought to this philosophy. They defined solely by their numbers what is a melodic interval and what is not, what is consonant and what is dissonant, thus doing violence to the natural judgment of the ear."
His theory of harmony thus had to include thirds and sixths, since they were used in modern practice. However, Kepler didn't believe, as Vincenzo did, that the true cause of harmony could be found in the physical properties of sound. He thought that the explanation for consonance was geometric, and constructed an elaborate argument about polygons to support this view. The geometrical figures of music were recognized by the geometrical archetypes in the human soul. Kepler was thus still at heart a Neoplatonist. Geometry, rather than arithmetic, was the ultimate cause of all phenomena. This principle applied not only to his music theory, but also to his astronomy. From a modern perspective, Kepler's practical music theory appears unproductive and even wrong, since he avoided any detailed empirical investigation of pitch. Kepler wasn't a musician, however, and it's clear that he was much more sensitive to the relationship between mathematical theory and physical phenomena in the field of astronomy. The idea of cosmic harmony was vital to Kepler's astronomy. You saw in Unit 7, Section 1, how pleased he was that he could explain why the Creator had used precisely 5 regular solids to produce just 6 planets and their orbits. Here is a clear illustration of his Neoplatonism. Believing that God created the universe according to geometric principles, he tried to fit his astronomical data into a suitable scheme. In the case of music, he was satisfied with his first model. However, as you saw previously, Kepler went on to regard his planetary model as insufficiently accurate in the light of new data. This didn't mean that he rejected his Platonic scheme, Indeed, he was convinced that he simply had to find the true harmony of the planets. Kepler found his harmony in the shapes of the elliptical orbits he discovered. To be precise, the harmony wasn't in the ratios of the longest to the shortest axes, but in the angular velocities the planets had at those points. He observed that the ratios of these velocities was, for each planet, strikingly close to a musical ratio. Saturn's ratio, for example, was 5:4, a major third, while that of Mars was 3:2, the fifth. Kepler produced the following argument. When a planet is nearest to the Sun, it's travelling at its fastest speed. It gradually slows down as it moves away from the Sun, and is at its slowest the furthest distance away. Kepler stressed that his planetary music was metaphorical. Taken literally, however, the result is this collection of planetary music. First, Saturn. Jupiter. Mars. Earth. Venus. Finally, Mercury. The motion of all the planets combined could produce a true celestial polyphony. Kepler believed that this was mirrored in real music, and that both led towards an understanding of God.
The motions of the heavens, therefore, are nothing else but a perennial concert, rational, not vocal, tending towards definite and prescribed cadences, and by these marks distinguishing and articulating the immensity of time, so that it's no longer a marvel that at last this way of singing in several parts, unknown to the ancients, should have been invented by man, the ape of his creator, that, namely, he should, by the artificial symphony of several voices, play out, in a brief portion of an hour, the perpetuity of the whole duration of the world, and should, to some degree, taste of God the Creator's satisfaction in his own works, with the most intensely sweet pleasure gained from this music that imitates God.
Kepler's ideas mark a high point in the revival of Neoplatonism and theories of universal harmony. In the course of the 17th century, the type of question that was now being asked by most scientists eventually undermined the whole philosophy of harmony. Instead of seeking ultimate causes of things, they were concerned with actual experience, quantification, and measurement. I'll concentrate on the purely musical aspects of this process and return to the investigation of the problem of pitch. A major figure in this transformation of ideas was Vincenzo Galilei's son, Galileo. He too was a competent lute player, and it's likely that he acquired his habit of experimenting from his father. Galileo put his ideas about sound into his Discourses Concerning Two New Sciences of 1638, but he probably reached his conclusions much earlier, since by then he was 74. Galileo's greatest insight was that it's the characteristic vibration of a plucked string which gives it its sound. He knew that the pitch of a string is determined by the frequency of that vibration, but he was unable to describe the vibrations in any detail. However, it's in this work that we first encounter aspects of the theory of sound that require mathematics for their elucidation. There are two related problems. The motion of a vibrating string must be analysed, and the connection between vibration and pitch must be established. What concepts are needed, for example, to describe a string vibrating in a mathematical way? Which of these account for the note it emits? Can these be quantified? These were new questions being asked, and they were to call for new mathematics. By the mid-1630s, the key physical factors related to pitch were known to several investigators. These were the length of string, tension in the string, thickness of the string, and materials of the string. What was needed was a formulation which would explain mathematically how these factors combined to produce a note of given pitch. The step from observational physics to mathematical physics was taken by one man, the French minim friar Marin Mersenne. A religious man, Mersenne was a Neoplatonist in that he believed God constructed the universe according to number, weight and measure. Significantly, his most important publication was called Universal Harmony and included practical music as well as the mathematical sciences. However, unlike Kepler, he didn't think it was possible ever to achieve ultimate knowledge or certainty. All that men could do was observe and experiment with natural phenomena. He spent a great deal of time performing acoustical experiments, measuring the speed of sound and investigating the properties of musical instruments. Through his books, his enormous correspondence and his numerous experiments, many people came to take the physics of sound as an object worthy of further serious study. The outcome of his research into vibrating strings was the law you'll find in the cassette notes. The pitch of a plucked string is directly proportional to the square root of the tension. It's inversely proportional to the length and inversely proportional to the square root of the diameter. Mersenne wanted to know why the law he had found appeared to be true. In 1645, he wrote to Torricelli suggesting he try to prove that the frequency of the vibration is directly proportional to tension, using a mathematical theory of the vibration of a string. Torricelli doesn't seem to have replied. In the next year, he wrote to the young Christian Huygens, who was then only 17, with another similar question. Mersenne probably didn't realise how hard his question was. Huygens could only reply at that time that he was already interested in the problem, but didn't know how to answer it. One of the first adequate answers to Mersenne's problem came from Brooke Taylor in England in 1713, who had the calculus available. That success indicates how closely calculus and physics were to become, and reminds us how long even the mere description of motion defied contemporary mathematics. Mersenne, of course, recognised that his theory was far from accounting for all properties of a vibrating string or pipe. He said of his law that
it does not follow that other cylindrical bodies or other shapes should have the same relationship to sound as strings, as several have believed up till now. I show this by very exact experiments that we have done several times in the presence of excellent geometers and a musician, whose ear is very expert and refined.
Mersenne was aware of the existence of overtones in a string, but he could not adequately explain how a string could produce different sounds either singly or simultaneously. He thought about the problem a lot, which he called the greatest difficulty that I have encountered in music, and wrote to Descartes and Constantine Huygens on the subject. He observed that an open string makes at least 5 tones at the same time, but how several tones could be produced simultaneously seemed impossible to imagine. Christian Huygens was also baffled by the problem and could do nothing with it. The problem of overtones was given a new lease of life in England over 20 years after Mersenne's death. In 1677, the Oxford mathematician John Wallis wrote a letter to the Royal Society describing an illuminating experiment he'd recently heard of. In about 1674, 2 musicians in Oxford had festooned a string with small paper rings and made it emit a harmonic of its fundamental tone. Most strings vibrated vigorously with the string, but some stayed fixed. By making visible the otherwise too rapid motion of the string, the rings showed that some points of the string did not vibrate. It's as if the string had been clamped there, and Wallis found the ratios of true lengths to these shortened lengths were in accordance with the harmonies involved. These stationary points are now called nodes. The string will vibrate naturally in any of these ways, which are the physical source of the harmonious intervals. Wallis's letter thus opened up the explanation of Mersenne's problem for future study, but even he didn't consider the idea that these musical tones could be emitted simultaneously. What was required was a mathematical description of the vibrations of a taut string. Such a theory was found in the early 18th century and will be described later in the course. What's significant here is to note the transformation of musical science in the 17th century from a priori Pythagorean arithmetic to a branch of mathematical physics. This began with the physical formulation of the question of sound emission by Galileo, its experimental resolution by Mersenne, and then the search for a mathematical explanation. Such a search obviously influenced those, like Huygens, who were both experimentalists and mathematicians, to look for a more useful mathematics than classical static geometry. It also provided an opportunity to claim the usefulness and legitimacy of mathematics by showing that it could yield demonstrable truths. But there was a negative side to this advancement in vibration theory, one which affected attitudes towards both music and the broader concept of universal harmony. By investigating the problem of pitch in such detail, in abstraction from any musical context, the meaning of music was ignored in favour of an analysis of motion. The effects of music on the listener were considered to be purely mechanical or physiological, being explained in terms of vibration. This mechanistic theory contrasted with Neoplatonic explanations, which were more concerned with the spiritual and metaphysical dimensions of music. In the course of the 17th century, the status of harmony was gradually demoted. It became a subsidiary property of sound, no longer a basic category of analysis. At the same time, the quadrivium lost its force in education. By around 1700, the distinction between the objective science of sound as rational mechanics and the subjective art of music was clearly drawn. The idea that music somehow provided an insight into cosmic truths no longer appealed to most natural philosophers. This statement, like most generalizations, has its exceptions. Neoplatonic philosophy was not entirely overthrown. Perhaps the last, and certainly the most important natural philosopher in the late 17th century to find inspiration in Pythagorean ideas was Isaac Newton. It was an aspect of his work which remained unknown until this century. Like most of his contemporaries, Newton considered musical sound in terms of vibration. In fact, he was the first to attempt a mathematical and physical analysis of waves in a compressible medium. Newton knew very little about the practice of music and never seems to have played an instrument. However, this didn't prevent him from speculation about the importance of proportion. Newton, like Kepler, was convinced that the universe was constructed according to mathematically discoverable laws, a form of harmony. It was this concept which guided the discovery of his 3 laws of motion, first published in his Mathematical Principles of Natural Philosophy in 1687. In an unpublished manuscript version of a later edition of this work, Newton suggested that Pythagoras had himself known of the inverse square law theory of gravity and had hidden it in the story of the hammers and their production of musical sounds. Newton believed that the true harmony of the spheres, expressed in the inverse square law, had remained hidden until he, Newton, rediscovered it. Such a belief made Newton, like Kepler before him, a true Pythagorean. Thus, while music may have been studied in the context of acoustics in 1700, world music lived on, finding new expression in the Newtonian laws of mathematical physics.